All right, that's not bad. That'll work. All right, problem 6. Lab has found it takes 10 newtons of force to break free a 2 kilogram block of wood from the lab table and 8 newtons to keep pulling it at a constant speed. All right. Determine the normal force acting on the block of wood. So first thing you do with that is you draw a force diagram, right? Fn, Fg, you got some force of a pull, and some sort of force of friction, right? So the pull and the friction are the same, normal force and gravity are the same in magnitude, right? They're obviously not the same exact force, they're just the same magnitude because they cancel each other out, right? So the normal force has to be equal in magnitude to gravity. Gravity is equal to mg, right? We were talking about this last week. You got to be quick at calculating this. The quiz, right? You got to be quick at calculating this force of gravity. mg, 2.0 kilograms times about 10. We just use 10. Don't worry about 9.8 on short answer problems. You can always just use 10. Often on multiple choice questions, it's 10 as well. 10 newtons per kilogram. Because it's usually the answer's approximately or closest to, it says something like that. So you can use 10 newtons per kilogram. A few of you on the quiz, going back and looking at your short answers and stuff, what you did was you were putting in the weight. If I gave you the weight in newtons, some of you put that in for n. So don't do that. Mass is kilograms. Force and weight, force of gravity is literally weight. Those are both in newtons. So make sure that's going in for the force here. That was a mistake you were making. All right. So 2 times 10, it's 20 newtons. You don't need to show this calculation out for this type of problem, right? Kind of moved on to the next phase here. So, normal force, and since this is going down, this has to be negative, right? This is also, the beginning of Worksheet 5 is kind of related to this as well, right? The up and down forces have to balance each other out. The left and right forces have to balance each other out. So if this is negative 20 newtons, the normal force must be positive 20 newtons. The positive sign matters because that's the direction, but for calculating friction, which is the next part here, so in the next part, we are going to calculate the coefficients of friction. When we use the friction equation, the sign on the normal force doesn't matter. We drop that. So in that formula, force of friction equals the coefficient times the normal force. The normal force, it's really just the magnitude of the normal force. So I'm going to leave the force diagram up here. I'm going to get rid of all this calculation mess here. I'm going to leave this here, negative 20 newtons. So determine the coefficient of static friction for the wood on lab table interface. All right? And again, don't go to that reference table and say, okay, lab table, that's like wood, right? So it's wood on wood, I'll just look up the coefficient. No, don't do that. The materials literally have to be what is written on that little chart in order to be used. You don't use that chart unless it's literally giving you the two materials. This is literally giving us the lab. This is for mica, the lab tables, for mica. Actually, I don't know what that material is back there. It's like some sort of synthetic. All right? So, coefficient of static friction. So, force of friction equals coefficient times the normal force. All right? Well, coefficient is what we're looking for. All right? We're looking for, we're going to put in the 10 newtons for the force of friction for the static calculation. That's how much it takes to break it free. Right? So the force of friction here is 10 newtons to break it free. Coefficient is what we're looking for. The normal force is 20 newtons. And you don't need the sign on this. This is just the magnitude of the normal force. All right? Just the magnitude, however big it is. So 10 divided by 20. Right? Divide both sides by 20. The units cancel. And you get a coefficient of static friction equal to 0.50. There's no units on that. Basically, the way you read a coefficient, it's like the percentage of the normal force. So the force of friction is half of the normal force, basically. So if this thing weighed 100 newtons, the force of friction would be 50 newtons, static friction. It would take 50 newtons to get it moving. All right? But once it's moving now, it only takes 8 newtons to keep it moving. So remember in the lab, we pulled that block, it broke free, and then took a little less force to keep it moving. All right, so now what happens is we take a look here. It's still, the force of gravity and normal force is still 20 newtons. But now we're sliding it at a constant velocity. The force of the pull now is positive 8 newtons. That means the force of friction has to be negative 8 newtons. I guess I didn't clarify that. The force of the pull right now is positive 8 newtons, therefore the friction has to be negative 8 newtons. Now we solve for the kinetic. Force of friction equals mu times normal force. We don't put the sign, this is magnitude also. Both of these are magnitude. The signs don't come into play when you do this calculation. So 8 newtons equals coefficient times 20 newtons, divided by 20 newtons, divided by 20 newtons, cancels, the units cancel, you get a mu of 0.40. All right, that's the coefficient of kinetic friction. That's it. This is your main equation. The one problem you do have to watch out for is if I ask you for the static friction on something, force of static friction acting on something, you've got to be careful not to immediately try to use the equation. For instance, if I push on this calculator here with a force of 5 newtons and it stays stationary, then the force of static friction has to be 5 newtons. If I push out with 10 newtons and it still stays at rest, the force of static friction has to be 10 newtons. All right? The force of static friction equals whatever is being applied to the object. So if you know something's not moving and you're pushing on it, then the force of static friction, no matter what the coefficient is, the force of static friction just has to be equal to whatever the push is. All right? So one mistake kids will make is, well, not kids, but students in general will make is they will see the materials, wood on wood, and immediately start doing the calculation. You don't need to. If you know it's not moving, friction just has to equal the push. All right? All right. So let's take a look at Worksheet 5. Any questions on that? Friction? Don't be shy. Any specific ones? Those first few questions, don't worry about those. We're worried about using that equation, all right? And determining coefficient. You could have to determine any one of these, right? Typically, we don't determine the normal force. Usually, we know the mass of the object, right? Throw it on a scale, we're given. Usually, we're doing this. Sometimes we're just asked questions like, for instance, look at the table right now. Look at the chart. Sorry, not the table. The chart of the coefficients. Back on page 2. All right? Let me zoom in here. Sometimes we're just asked questions like, all right, just kind of qualitative questions. Okay, which coefficient, which material combination is has a higher friction, right? Wood on wood or steel on steel. Well, steel on steel has more friction than wood on wood. And you just compare the coefficients. So sometimes you're asked to do simple stuff like that, okay? Stuff that's not that big of a deal, interpreting this table. This is one of the rare tables on the reference table. There's not really, most of the physics reference table is simply equations and lists of constants. This is one of the rare tables in the reference table that you can actually read and answer questions. There's really usually not many. And again, if there's nothing listed here, you just use the same value. All right, just use the same value. Actually, you know what? I thought about the other day. I wonder actually if they need it to be the same value this way, but they must not because there's none listed here. So it must be the same value. I don't know why they just don't type it again, but it's always been that way on the reference table. All right, so let's take a look at Worksheet 5. It's kind of a introduction to angled forces. I think the first question is pretty straightforward, right? This one here. It's that second question that gets kind of wacky. So again, I have the solutions for this are posted. Definitely want to check those out, read these solutions. We'll talk about it now. I'm not going to draw every single one right now. I almost feel like I'm insulting your intelligence with this a little bit, but it is what it is. So it says, determine the magnitude and direction of the forces required to balance these following situations. Sketch emission forces in with a vector and a label. The whole point here is just to get you thinking about how forces have to balance, right? So if 6 newtons is pulling up and 4 newtons is pulling down, but somehow this is balanced, there must be a force we don't see here, right? There's got to be another negative 2 newton force going down there. So in the video, it's nearly impossible to see, but follow along with the solution. Here, negative 3 newtons, right? There must be a positive 3 newtons balancing that out. In fact, there's actually an infinite number of ways to answer these questions, right? Because you could make a rope going this way and this way, balance it out, but that's not what I'm looking for. I'm looking for all on-axis forces, meaning forces that line up with this axis. Negative 3 plus 1. So I just said I wasn't going to do them all, but it must be a plus 2 newton force going up here. All right? We've got 13 total going up. There must be a negative 13 newton force going down. This one here. Okay, so this one's a little different. We have 2 axes going on here. And all it is you must have a negative 8 newtons going down, you must have a negative 12 newton going to the left. It could be one rope going this way, one force going that way, but we're not there yet, okay? We're going to get there in this next worksheet, on the next problem, and then the problem after it. This next one, we have total of 18 going up, so we have to have a total of 18 going down. We've got negative 5 to the left, positive 10 to the right, so there must be another negative 5 to the left here. What are we, 35 or 29? All right, so those are our forces there. All right, any questions on this first one? We're just getting our feet wet with trying to figure out how forces cancel each other out. No questions? All right. All right, so immediately I throw you into the snake pit on this next one, you know? I don't really have a great other way to do it. I guess I could introduce the whole trig thing first. All right, and I think maybe I will do that just kind of right now. So we have this next problem. All right, so this is the first time we see a problem like this, where we've drawn force diagrams of angled forces, right, of ropes and stuff. We haven't done any calculations with them. 50 kilograms of books in a box. It's on the ground, the rope tied to it. Mover's trying to pull the box along the ground, but can't get it to move because of the heavy weight and the amount of friction. So everything's stationary. All right? The mover is pulling on the rope with a 300 newton force. How do they know that? I have no idea. They just take it for what it is. It's 300 newton force. At around a 30-degree angle with respect to the ground. Draw a force diagram for the forces acting on the box. Keep in mind that you must use forces which are not necessarily listed in the problem. All right, so this is why we spent all that time drawing force diagrams, so that you could identify all the forces. If you don't identify all the forces, you're not going to end up doing the problem. All right, so let's draw the force diagram. All right, so the dot represents the box. All right, some obvious forces first. we definitely have the force of gravity pulling down this box, right? That always is present. We definitely have this rope pulling on the box with 300 newtons at an angle of 30 degrees. So I'm going to include that in my force diagram, the angle. All right? Maybe I should give that a name rather than a number, right? Maybe I should say, okay, this is the force of the pull. Or typically if it's a rope, we call it a force of tension. All right? That's equal to 300 newtons at an angle of 30 degrees. Okay. Now, what other forces must I obviously have? Maybe not obvious, but what other forces do I have? What do you think? Anybody? What's that? Normal force. Yes, the ground is it's touching the ground. It's touching the ground, so there's got to be normal force. All right. What else? It's got to be a frictional force because it's not sliding left and right. Something's holding it back. All right. So I put this on a coordinate system. So I need the reference. This is the positive x. This is the positive y-axis. This is negative y-axis, negative x-axis. We don't need to label this axis because it makes it look busy, right? It makes it too complicated. So for now, I'm going to put it on there. The reason we do this is so that we can kind of look back at the first problem on this worksheet, right? And we can say, okay, the x forces must balance out. The y forces must balance out. However, this one's not on an x or y axis. That's the problem. All right, that's the issue at hand. This force, it says, is all the movers 300 newtons of applied force going in to try to move the box to the right in the positive x direction? How can you tell? Well, no, it's not because it's at an angle, right? This rope is also pulling up. So it's pulling horizontally, this rope, this tension, but it's also pulling vertically. All right? What's that? You right back there?
Yeah.
Oh, your seat just break? You literally just broke the stool. How did that happen? Where'd it go? Where'd the foot go?
It's like snapped in half.
Well done. Nice job. Thanks.
My bad.
It's fine. I'll figure it out. Those things will pop off. But now it's crooked, right? Anyway, so here's the trick. How do we figure out how much force is pulling horizontally and how much of the force is pulling vertically? All right. This is interesting, right? In this case, the normal force does not just equal gravity because the rope is also pulling up. So what we got to do is we got to take that rope and break it into components. So again, I worked through this whole problem in the video, and I encourage you to go back and watch that. I'm not going to go exactly through each step right here, but I'm going to kind of do the whole, I am going to do it right now for you and get you kind of up to this phase here. All right. So let me mute this for now and give myself a little more board space. All right, and just kind of talk about this problem. So I want to make this look like one of the problems in problem 1 eventually. Again, I encourage you to go back and watch a previous video where I actually walked through this problem. Right now I'm going to kind of show you how we just do it all at once, not in all these steps, right? So ultimately what we need to figure out here is how much friction and how much normal force is there. All right? Gravity, we know. What's the weight of that box again? 50 kilograms, was it? All right, so Fg is negative 500 newtons. Since Fg is negative 500 newtons, then up forces have to balance that out. All right? So now what the heck do we do with this 300? Well, here's what we do. We take that 300, we make a triangle out of it. All right, and this is on the next page. So that 300 newtons at an angle of 30 degrees, all right, has what we call an x and a y component. All right, the x component is, let's call this ft. We'll call this ftx. The x component is the projection of that vector down on the x-axis. The projection. So it's the, if I shine a light from above and I made a shadow, it would be the length of the shadow on the plane, on the x plane. All right. This one is the y component. Now, I draw them as these dashed vectors because they're not extra forces. Right? They're not extra forces. They are the amount that the tension pulls vertically and the amount that the tension pulls horizontally. All right? They're not new forces. That's why there's these dashed lines. You know? They're like virtual forces, so to speak, like ghost forces, shadow forces, something like that. Right? So if I shined a light from this side, the shadow of this vector on this plane would look like that. You guys kind of visualize that concept? I like to think of it like that. And here's the cool thing. This is why you learn trig, I would argue, myself. Math teachers might take offense to that. I gave the 8th graders a little talk about y equals mx plus b there, finding slope and y-intercept. So I said, hey guys, you know, the reason you do this is because x, y, mx, and b are all physical quantities of some kind. A couple of them nodded their heads politely. A couple just kind of, you know, it was fun. I like getting those young kids once in a while. All right, so check this out. This used to be part of math class, where you get a vector. This used to be part of trig back when the great Mr. Lavecchio taught it, which some of your older siblings may have remembered him. But it used to be part of the curriculum, and you have to take a vector and find its x and y components, right? For you guys, I'm guessing this is the first time you've seen this, right? Is this true? Yeah. So the standard procedure here is to make a parallelogram out of it, right? Which in this case is a rectangle. And then the height of this triangle and the base of this triangle end up equaling the components of this vector. All right? So we have to use good old SO, COB, and TOA here. All right? If I want to find the length of this side of the triangle, the length of this side of the triangle, it's gonna get it done for us here. All right. So now, some people will make it two different triangles. I don't recommend doing that. This FTY, it's the same length as this side of the triangle here, right? So I usually would just write FTY over here. And then I'm just dealing with this triangle. So let's sine of theta equals opposite over hypotenuse, right? So sine of 30 equals, here's the opposite, it's FTY over hypotenuse, which is 300 newtons. So these vectors' length is proportional to the strength of the force. So if I find the length of this vector in terms of newtons, I know its strength. All right, so now I have to solve this for FTY. FTY equals 300 times the sine of 30 degrees. And again, I go through this all in the last video. I'm probably not going to have time to completely finish it. 300 times the sine of 30. Sine of 30, you might remember being 1/2. That's 150 newtons. So this force goes upwards with a strength of 150 newtons. So immediately, I know that the normal force has to be 350 newtons. I don't even need to show any math for that. I just know that these two have to add up to equal 500 to balance out the force that's going down. All right? And that is the essence of static force problems. We're doing static forces in AP Physics C right now, and some kids are having trouble with it. Ultimately, it all comes down to making sure that the up and down force is balanced and the left and right force is balanced, just like problem number 1. But if you have a force at an angle, you got to break it down into its components. And then you can go and make sure things balance. All right? For the x direction, we'd say cos of theta equals ftx over 300 newtons. Multiply both sides by 300. So ftx would be equal to 300 times the cos of 30 degrees. And somebody have the answer handy? I forget it.
260.
260? That's about 260 newtons, that x component of the force. So this pulls horizontally, right? Ftx is 260 newtons. Therefore, what does the friction have to be equal to? Yeah, negative 260. You got it. Negative 260 newtons. So the angled force, you just can't add into the mix like, 300 plus 150. 300, mistake kids would make would be like, all right, 300 newtons going up, 500 newtons going down, so that's going to be 200 for the normal. No. You got to break it into its components. And then also, how do these three quantities add together? The ftx, so if you know this is, Pythagorean theorem, all right? If you want to, sometimes you're given the hypotenuse side, you got to find the other one, okay? Pythagorean theorem.